It is quite possible that the tRNA is the most epically awesome molecule ever. It has an incredible overall structure in which the single-stranded RNA wraps back upon itself and it forms 4 very distinctive arms. And when these arms form their 3-dimensional structure, it literally gives the tRNA a kind of L shape or even liver shape. And so it's got overall 3D structure. And it allows for each of these arms to sort of have a distinctive role that they play. And none of them is more important than the anticodon arm. So the anticodon arm, as you might have guessed, is the arm that recognizes and hydrogen bonds with the codon. So that must mean that the anticodon must be going anti-parallel to the codon. So where we know that the mRNA is actually synthesized in the 5' to So where we know that the mRNA is read in the 5' to 3' direction, we recognize that the tRNA anticodon has to be in the opposite or anti-parallel orientation. So this has to be the most 3' nucleotide right here, this U, and this has to be the most 5' nucleotide right here, the C, so that it's traveling anti-parallel to the mRNA, and then pairing hydrogen bonding with the codon. So of course U will pair with A, and C will pair with G. So notice that our codon is AAG. So if we want to look up AAG in the codon usage table, that will enable us to determine what amino acid the tRNA carries. Francis Crick termed tRNAs adapters, and you can really see how that is such a genius term for this, because notice that the anticodon arm, by binding to the codon, is adapting the mRNA to the polypeptide chain, that is, to the amino acid. So let's see if we can do a good job of being tRNAs by looking up the codon AAG in the codon usage table and finding out exactly what amino acid this particular tRNA carries. So notice AAG, lysine, the basic amino acid. So attached to what's called the acceptor stem of the tRNA, we get the amino acid lysine. Lysine is first attached onto the tRNA in a step that's called activation. In fact, technically, we could say that the very first step of translation is activation of the amino acid. So, of course, it would be activation of the N-formyl methionine because it's always the first amino acid. But the first thing that has to happen to that amino acid before it can be added onto the polypeptide chain is to get put onto the tRNA so that the tRNA can deliver to the ribosome and adapt to the mRNA. So the amino acid getting added onto that acceptor stem is very, very important. And I think Sam is going to appreciate this. I know, Sam, you've got a lot going on with religious studies, and you're also probably have a pretty good historical orientation. And so this is going to strike you as interesting. Lysyl tRNA lyse is the name of this particular tRNA. And I think of this in terms of a kind of medieval orientation. That is, a tRNA that is destined to carry lysine is called tRNA lyse. A tRNA that is destined to carry lysine and does carry lysine is called lysyl tRNA lyse. It sort of like reminds me of medieval knights. So in any case, lysyl tRNA lyse is the name given to this entire structure because it's a tRNA that's supposed to carry lysine, and it does because it has bound to and activated that lysine. So notice that in addition to the acceptor stem and the anticodon arm, arguably the most important parts of a tRNA, there are 3 other arms. There's a D arm, and there's a T-cy-C arm. The T-cy-C arm is known for having very unusual nucleotides, such as ribothiamidine and pseudouridine, so very unusual nucleotides in that area. And right here is what's called the variable arm, and the variable arm literally varies in length. Sometimes it's longer, sometimes it's shorter. So that is the other arms that you see on a tRNA. So I think it's a good idea to practice just a little bit more so that we can understand how anticodons relate to codons, which literally then relate to the adaptation to an amino acid. So let's practice. What amino acid does the tRNA carry if it has the anticodon sequence 3' GCG 5'? So I find that the best way to do this is to write this out. So you've got your acceptor stem, your anticodon arm. So I'm writing an anticodon arm, and it has the sequence GCG. So then we know that that would recognize the codon CGC. And then we can look up CGC in the codon usage table and determine what amino acid would be carried by that particular tRNA. Now, the only thing that complicates this is that usually tRNA sequences, like all nucleotide sequences, will be listed 5' to 3'. So if it's listed 5' to 3', you have to remember that the anticodon always aligns 3' to 5', so that it can be anti-parallel to the 5' to 3' codon. So you have to be thoughtful, use your sexy mind, and wake up out there and stop falling asleep, because I do have my squirt gun. Okay, so let's go ahead and move along, making sure that we know what GCG anticodon, what it would recognize. Remember that it aligns with the codon CGC, so we can look that up, CGC, and there it is, the pirate amino acid. This is the actual three-dimensional structure of a tRNA, and you can see the acceptor stem is in this area. So as the three-dimensional structure ensues and you get a little bit of this local double-stranded helical kind of region, things look just a little bit different. You get more of that L shape rather than the sort of like clover shape that we saw when we flattened out that structure. I will often show the flattened out structure just for clarity, but do bear in mind that this is the actual three-dimensional structure. So it might be tempting to think that because there are 64 codons, or at least there are 61 codons that encode for amino acids, it might be very tempting to think that there must be 61 tRNAs out there. But as it turns out, there are not. There are far less tRNAs than there are codons. So what this means is that part of the root of degeneracy lies in the fact that more than one codon can be recognized by a single tRNA. That is, some of the loosey-goosiness that we see in the most 3' position of the codon must stem from the most 5' position of the anticodon being a little bit flexible. So let's make note of that. There are not 64 tRNAs. Partly that is because there are stop codons, but partly it is because tRNAs can recognize more than one codon, and that is to say that they have some flexibility. They can have a little promiscuity with their most 3' nucleotide, or with the most 5' nucleotide of the anticodon, the most 3' nucleotide of the codon. So let's totally check out an example of this. Looking at the anticodon 3' CCG, we would understand that the flexibility must occur in this G. That is, this G must be able to loosey-goosey pair. We know that typically it would pair with a C, right? But maybe it can recognize something more than just a C. Maybe it can loosely pair with something else. Let's see if we can guess what it might also pair with. So CCG would typically recognize the codon GGC. So let's see that codon GGC, GGC, okay, GGC, glycine, right? But notice that GGU, GGA, these all encode for glycine. So maybe this anticodon can recognize more than one of these codons. And in fact, it recognizes both GGU and GGC. So the tRNA with the anticodon CCG can recognize 2 of the 4 codons that encode for the amino acid glycine. This is really cool because what's going on is just that little bit of flexibility in the pairing between the G and the C, so that the G is like, why not a U? And it can pair with that U as well. CCG can pair with GGU and GGC, showing just a little bit of flexibility in this pairing, and this is called wobble, the probably raddest term ever. And if you're really feeling sexy-minded, you could say that wobble is a big part of what leads to degeneracy. Try that on your next date out for size, right? Hey, and Allie and Katie, stop making out. I do have my squirt gun. So let's go ahead and move along, because we are now ready and poised to talk about initiation of translation. And don't forget that just like transcription, there is an initiation phase, an elongation phase, and a termination phase of translation as well. Beginning with initiation, I want to make a quick statement that relates to the extra credit question that I asked you on the Vodcast last time. So in prokaryotes, translation begins while mRNA is still being transcribed. So this is a very cheesy picture to try to show you that, in fact, what could occur is that DNA could be being read by the RNA polymerase enzyme. So just to reorient ourselves, this is DNA, right? This is the DNA, okay? So DNA is being read by RNA polymerase. This is RNA polymerase. And that RNA polymerase is synthesizing, as it always does, the RNA, and in this case, obviously, it's mRNA, because simultaneously, as that mRNA is being made, the ribosome has aligned with its AUG start codon, and it has begun making polypeptide chain. So this polypeptide chain is escaping out of the top of the ribosome, and we're getting the synthesis of the polypeptide chain at the exact same time as we're seeing the synthesis of the RNA. So the question then becomes, why is this only possible in prokaryotes and not in eukaryotes? And it relates to the last extra credit question that I asked you about. So I want you in your extra credit, and remember, I don't want to receive those until the very last vodcast. After the very last vodcast is over, you can start emailing me those extra credits. But recognize that this process is only possible simultaneously in prokaryotes. And I want you to tell me why it's only possible simultaneously in prokaryotes. And then I want you to tell me why that relates to the first extra credit question that I asked you. I'm like pushing you with the sexy mind today. So with initiation, we're going to begin at the start line. Remember how the promoter provided the start line for transcription? Well, it turns out that there is a start line for translation as well. And this start line is epically named the Shine-Dalgarno sequence. I really think we should actually rename it, because I hate it when things are named after scientists with an ego. Pompous, pedigree, pickled professors. But in any case, the Shine-Dalgarno sequence is what it's called. That is the start line of translation. It is where everything gets ready to go, gets ready to read the mRNA. So at the Shine-Dalgarno sequence, we know already that it is the 16S ribosomal RNA that binds to this start line sequence and orients the mRNA such that the AUG start codon is aligned just right to serve as the initiation site. So as soon as the 16S rRNA inside of the 30S subunit aligns with the Shine-Dalgarno sequence, everything else can be aligned. Now, I think it's important that we really understand this well. So I'm going to make a blow-up drawing. I want to actually show you in a bigger picture what this looks like. So inside of the 30S ribosomal subunit, so this is a very big picture of the 30S ribosomal subunit. And then let's get our mRNA going on right here. And we know its 5' end is over here. and then you've got the 3' end over here. And we know that when the 30S ribosomal subunit binds, the AUG start codon is aligned just perfectly to allow for alignment with the anticodon on the tRNA carrying N-formal methionine. But then upstream of the anticodon is the translation start line, the Shine-Delgarno sequence. It is a very purine-rich sequence. So remember, A and G are the purines. So AGGA is the sequence, or something of that similarity, that is the Shine-Delgarno. So that Shine-Delgarno sequence pairs with, inside of the 30S ribosomal subunit, you find the 16S rRNA. And this 16S rRNA will have on it, okay, it's going to run anti-parallel to the mRNA. It will have a very pyrimidine-rich sequence that pairs with the Shine-Delgarno. So this is literally aligning and orienting the 30S ribosomal subunit with the Shine-Delgarno sequence, enabling the AUG to be in just the perfect spot to bind with the tRNA carrying the F-met residue. And this is a big part of initiation of translation. So the AUG start codon is aligned just perfectly with the initiator tRNA carrying the F-met. This enables full composition of the initiation complex. So we get the multiple things involved with this, the 30S ribosomal subunit, the mRNA, the tRNA with the F-met, but notice too that there are some factors called initiation factors. These initiation factors are very creatively named IF1, IF2, and IF3. So IF2 is perhaps the most important of the initiation factors. What it does is it coddles the F-met carrying tRNA, and it makes sure that it's only ever the N-formal carrying tRNA that ever gets inserted first, aligning with the AUG start codon. So the IF2 plays the very important role of making absolutely certain that it is matching the N-formal methionine with the right AUG start codon, and never it makes sure that that's never the wrong initiator tRNA with the wrong amino acid. Now, notice that it's also bound to GTP. So GTP is going to provide energy for the beginning, for the snapping off or starting point of the initiation phase. We also have a couple of other initiation factors, IF1 and IF3. IF3 is pretty rad too, because what IF3 does is it makes sure that we don't see premature association of the 50S ribosomal subunit prior to the formation of this initiation complex. So this is actually really important. Notice that only the 30S ribosomal subunit is involved at this point, and it's not until initiation is completely finished that we see the 50S ribosomal subunit getting in and associating with the 30S to make the fully functional ribosome. So once initiation is kicked off, then we actually see the addition of the 50S subunit. And that's what happens in this next phase. GTP is hydrolyzed, it powers the addition of the 50S ribosomal subunit, and we see the initiation factors get the heck out of Dodge, and we are now primed and ready to go for the elongation phase of translation. So that is going to be our next focus, and you can gear up and get ready to go for the elongation phase. And don't worry, I still have my squirt gun. I also still have Rex, just in case you're wondering. In the last 2 minutes of lecture today, we're going to see if we make good ribosomes. So that is to say that we're going to look at this mRNA and see if we can scan down this mRNA pretending to be a ribosome, looking for the first AUG start codon. So recognize that this right here is the AUG, or is the Shine-Delgarno sequence. So although I didn't put a sequence in there, it would be a very purine-rich sequence. Shine-Delgarno, the 16S ribosomal RNA aligns with that, gets the AUG positioned, and if we scan down looking for that first AUG, there it is, bingo, sets the reading frame so that then this RNA is read in triplicates after that. Now do take note that the first AUG will specify F-met, N-formal, methionine. And then if we use our codon usage table, we can look up the next amino acid. So we look up the codon GUC and see what that specifies. And then notice we run into another AUG. This time AUG is just simply going to specify the amino acid methionine. So you can keep on going from here, seeing how good of a ribosome you make and deciding what the full sequence of that polypeptide chain is going to be. Don't forget that this is the most amino terminus, even though we know that it's formulated, and then that over here as it builds is the most carboxyl terminus, right? So this is always the direction of a synthesis, amino to carboxyl. Get good at being good ribosomes. You're going to practice this a lot more, I promise. And you know, somebody out there is going to have Rex to help them out. So I wonder who's going to get this.